And before we go for this today's session, we'll just have a look at the questions that have been asked in the yesterday's class. So regarding the yesterday's class, there were few questions that have been asked, like please explain the fourth problem diagrammatically along with the values. This is one question. And what is pipelining? Packet switching, is it connectionless or connection oriented? So first I'd like to answer this. Packet switching, is it connectionless or connection oriented? So in circuit switching, it is connection oriented, but when you go for packet switching, we have two types of packet switching. One is datagram switching, datagram subnet or datagram packet switching that we call it as, and the other one is virtual circuit packet switching. When you go for datagram packet switching, this is connectionless packet switching that we have, and when you go for virtual circuit packet switching is the connection oriented packet switching that we have here. And what is pipelining? So in the pipelining is what we call it, like you have a water pipe, say, when the water is flowing continuously, it will be flowing, right? So 1 liter you dump. After that 1 liter, if you are going to transmit another 1 liter, then between them, if there is a gap, that is one after other you are transmitting. But as a stream, if you are going to transmit continuously one after other, we call it as pipelining. And all these questions are related to the propagation time. What is propagation time? What is transmission time? Already this has been covered in the last classes. You just have a look at the previous videos. You can find what is this transmission time, propagation time. Transmission time and the transmission delay are the same, where when you have a frame, say for example 1000 bits that you have in a frame, so the time it takes to place the entire frame, to place all these 1000 bits in the frame onto the channel, we call it as a transmission time. So that depends on the length of the packet or the length of the frame. So all these bits have to be placed onto the channel. So it depends on the length of the frame. As well, it depends on the bandwidth of that particular channel. At what rate it is accepting the bits. That is the bandwidth. So it depends on, transmission time depends on the length of the message and bandwidth of the channel. So transmission time is defined as length of the packet divided by the bandwidth. And when you go for the propagation time, the time it takes for the first bit to start from the source to the destination. If it is between two nodes, any two nodes from the starting and reaching to the other end, we call it as a propagation delay. The time it takes for the first bit to start transmission from one end and how long it takes to reach to the other end, that is what we call it as a propagation time. So 2 times the propagation time is what we call it as a round trip transit time. So this propagation time, as we said, we need to transmit the data from the source to the destination. The first bit, how much time it takes to deliver from one end to another end. If for that you need to consider the distance between the two ends, and also you need to consider how fast the data is being transmitted to the other end. So the propagation time will be equal to the distance divided by the speed. That is the propagation time. 2 times the propagation time, we call it as a round trip transit time. So these are the answers for this, and please don't ask some silly questions like how to convert decimal to binary and all. So this is all what we have studied in our junior classes only. So please refer to some of your textbooks where you can find these sort of answers. But anyhow, I'll just explain you how you need to convert the decimal number into binary. So when you are converting the decimal into binary, binary is base 2. So divide this number repeatedly by 2. and then just get all the reminders. Read the reminders from bottom to top. Then you will be getting the binary value for this. So 2, when you divide 17 by 2, 8 is the quotient and 1 is the remainder. 2, then again you divide 8 by 2. 2 4s 8, 0 is the remainder. 2 2s 4, 0 is the remainder. 2 2s 2, 2 2s 1, and 0 is the remainder. So now you take all these bits in the upper direction, 1 0 0 0 1. So this is the binary equivalent for this decimal number. So, and the other questions were on the fourth problem, the problem 4 that has been asked. So I'll just refer to this. Again, I'll repeat this fourth question. So two hosts are connected via a packet switch with 10 to the power of 7 bits per second links. Each link has a propagation delay of 20 microseconds. The switch begins forwarding a packet 35 microseconds after it receives the same. If 10,000 bits of data are to be transmitted between the two hosts using a packet size of 5,000 bits. The time elapsed between the transmission of the first bit of data and the reception of the last bit of the data in microseconds is. This is what is asked. So what we told yesterday, first you need to find out the number of packets that you need to transmit. That you are going to get by dividing the total size of the message divided by the size of the packet. So 10,000 divided by 500. So the number of packets that you need to transmit is 2 here. After dividing 10,000 by 5,000, so you'll be getting 2. So what is given? Bandwidth is given to be 10 to the power of 7. The propagation delay is directly given. Someone has asked, how did you get this, how did you calculate this propagation delay in this question, like here? Why did you go for D into K as the propagation delay? As the propagation delay has to be equal to the distance divided by the speed. So that is the formula, but you have to look into the question, what is asked, whether the distance and the speed are given. But in this question, when you look at the propagation delay is D seconds per hop, that is given. For every hop, it is D seconds. How many hops are there? K hops are there. So to reach to the destination on this K hops, it requires D into K. That is the propagation delay. So you should not get confused. You need to check what is given in the question, and then you have to get the answers for this, right? So here I'll just have a look at this. So the propagation delay is 20 microseconds, and this is the bandwidth, and this is the size of the packet, and there is a waiting delay of 35 microseconds at the packet switch. So when you diagrammatically represent these two hosts and the packet switch, this is how you are going to represent that. A and B are the two hosts and S is the switch, let us assume. How many links are there? There are 2 links here. One between A and the switch and the other between switch and the B. So we know packet switching uses store and forward technique. So all the packets that are being transmitted by A will be stored over here at the switch, and then it will be forwarded to B. So here what is given? The bandwidth is given to be 10 to the power of 7, and propagation delay is given as 20 microseconds for each link. Each link has a propagation delay of 20 microseconds. That is, the first bit, when it starts from A, it takes 20 microseconds to reach to this S. This is one link to reach to this S. So that is transmission propagation delay per link, that is given as 20 microseconds. And it is also given the waiting time at the switch. Switch begins forwarding a packet 35 microseconds after it receives the same. So the waiting time at the switch is 35 microseconds. That is given. And then what is given? The length of the message is given, and the size of length of the packet is given. So length of the message is given as 10,000 bits. Length of the packet is given as 5,000 bits. So from this you calculate the number of packets. So the number of packets is equal to this message is divided into packets. So we are dividing this message into 5000 bits packets each. So 10,000 divided by 5000 gives us the number of packets that you are going to have here. So that is 2 packets that you are going to have. Now you calculate the transmission time for the first packet to reach to the destination. What does that involve? First the packet has to start from here. For that a transmission delay will be there where the entire 5000 bits of the first packet has to be placed onto the channel, onto this link. So how long it takes for this 5000 bits to be placed onto the link is the transmission time for the first frame. So that will be equal to the size of the packet divided by the bandwidth. So LP divided by B. What is the size of the packet? The size of the packet is 5000 divided by the bandwidth is 10 to the power of 7. So it will be 500 microseconds. So it takes 500 microseconds to place the entire message onto the channel. So the first bit, it has started at 0 times A. Then it takes, that is given as 20 microseconds it takes to reach to S. So subsequently all the bits will take 20 microseconds one after other to reach to S. So the propagation delay is 20 microseconds. So all the bits of this packet will be received to S by 500 plus 20 microseconds. By 520 microseconds, all the bits will be reached to the switch. There it waits for 35 microseconds. So once you reach the first bit, after that it waits for 30 microseconds. So it has to receive the entire frame and then it has to, the switch has to forward it. So it receives it after 500 plus 20 microseconds. So after 520 microseconds, the entire message will be received by the switch. So then it waits for 35 microseconds and then it forwards it to B here. So there again the entire message has to be placed onto this link which takes 500 microseconds again, and there is a propagation delay on this link also which is 20 microseconds. So the total time it takes for the first packet to be delivered from A to B includes 2 propagation delays, 2 transmission delays plus the waiting time at this node here. So this is how we are going to calculate the propagation delay, total delay in a packet switch network. Here it is a datagram network that we are assuming here. So the total propagation delay for the first packet will be 500 microseconds transmission time from A to S, and then 20 microseconds is the propagation delay, plus 35 is the waiting delay here, plus 500 microseconds to deliver the packet from this to B, and then 20 microseconds is the transmission delay, propagation delay from S to P. So it totals to 1075. That is the time that it takes for first packet to reach to the destination. So here when you want to calculate how much time it takes for the second packet to reach to the destination is immediately after placing the first packet onto the link, immediately A starts propagating the second packet here. So with a delay of 500 microseconds, the second packet starts forwarding, A starts forwarding the second packet here. So that takes, so these are all being done parallelly here. By the time 500 with the 500 milliseconds, after the 500 microseconds, the second packet has started. By that time it might have reached over there. After 20 microseconds it might have reached to this, that is first bit. When it has been transmitted, it takes 20 microseconds to reach to this. So after all the bits are being placed, immediately the second packet is also being placed onto the channel here. So it encounters a total delay of 500 microseconds only to be transmitted from A to B after B has received the first packet. Clear? I think it is cleared. So I'll just show you how this is going to happen here in this segment. You can see. So this is the time it takes for A to place the entire packet onto the channel. So this is packet P1. So this is placed onto the channel. It takes 500 microseconds. So for the first bit to reach to this S, it takes 20 microseconds. So this is the propagation delay. So total the last bit reaches to this S at 520 microseconds, right? 20 is the propagation delay, and it takes 500 microseconds for the last bit to be placed onto the channel. So with a delay of 520 microseconds, complete P1 first packet will be reached to S here. Then again it is encountering a delay of 35 microseconds. This is the waiting time at S for the first packet. After that, it starts forwarding the first packet to the destination. So P1, it takes 500 microseconds again to place the entire packet onto this second link, and it takes 20 microseconds to reach to the destination here. This is the propagation time. So total time for the first packet to reach to the destination is from here to here. So what is this? So 20 microseconds propagation time, 500 microseconds is the transmission time, then 35 microseconds is the waiting time at switch, and then 20 microseconds is the propagation time, and 500 microseconds is the transmission time. So this is the total time for the first packet to reach from A to B. And for the next packet, if you consider this is P2, immediately after transmitting the first packet, it starts transmitting the second packet. So with a delay of 500 microseconds, this second packet gets transmitted. So at every link, it will be encountering 500 microseconds delay only from that of the packet 1. So to reach to the destination, so once this packet is sent over here, parallelly you are transmitting this. So parallelly it will be encountering all this. There will be an overlap of this time over here for the second packet, and hence it has started 500 microseconds later to this P1, and it reaches to the destination after 500 microseconds. So every subsequent packet to this will be reached with a transmission delay only, so that the total time it takes for the entire message to reach to the destination is the time it takes for the first packet to reach to the destination plus the transmission time for this particular packet. So if you have the third packet, say for example, then after this 1000 microseconds, the third packet starts transmitting here. So to reach to the destination, it will be encountering 1000 microseconds delay. And hence for the nth packet, if you take, it takes n into tt. That is the time it takes to reach to the destination. So the total message can be reached to the destination with a proper total time it takes for the first packet to reach to the destination plus the transmission time here for the remaining packets. One after other you are transmitting. So if you have one, here in this case you have only one packet after this packet P1 that is following, so it takes 500 microseconds more. If you have total of n packets, so first packet takes this time, and the second packet takes 500 microseconds after this, and the third packet takes 500 microseconds after this, that is 1000. So the total will be this plus 1000. That is the total time it takes for the packet, for 3 packets consecutively being transmitted to reach to the destination. So for the remaining packet, it takes only the transmission time here. So this is how we are going to calculate the time it takes for the entire message to be transmitted from source to the destination. Here you have only one hop. If you have n hops, k hops here, then it will be k into the propagation delay that you are going to have here. Here you can see the propagation delay is added 2 times because you are having 2 links over here. So if you have k hops here, k links here, hops or k links that we have here, then it will be k into the propagation time. So that will be the answer for this. So here TP is the propagation delay per hop, but you have k hops like this. So for this hop it is P, for this hop it is P, and you have k hops here. So total propagation delay will be k into D. So that will be the total propagation delay. That is how you are going to calculate. Here you can see for all, here you have x by p packets here. So x by p packets, for the first packet to reach to destination, it takes this time. Kp by b plus dk. So this is the time it takes for the first packet to reach to the destination. And the remaining packets will be reached to the destination after one after other, after p by p. So for the remaining x, this number of packets to reach, so this will be n minus 1 into p by p. So this is how you are going to calculate the propagation delay. So someone was asking about subnetting, and someone has asked about the blocks. We'll see now. So in the last class, we were continuing our discussions regarding the IP addresses here. So the IP version 4 addresses are 32-bit addresses that we have, and the address space. What is this address space that is being asked? The address subnet mask. Subnet mask. Hello. Okay. All the subnets have a same subnet mask here. So this is the size of, so the size of the block that is requested is 16 with 16 addresses that is required. That is the size of the block. So the first, these are the contiguous addresses that are being allocated for this. And when we look at the first address, so this is the decimal equivalent for the first address. When you divide this by 16, it should be an integer divisible by integer multiple of the 16. So then if you can say that the size, this is how you are going to allocate the size of block here requested by an organization. So when you want to represent this making use of CIDR notation, generally an IP a block of addresses will be represented as this. So any address in that particular block, any one address in the block followed by a slash and this n. So this slash n is the mask that you are going to have. So this mask is nothing but, here you can see these bits are common and the other bits that is being varied is in these. Out of these bits also, if you represent them in the binary, these are the binary representations. Here you can see that up to these locations, it is common for all these blocks here. The first 3 bytes are common, and in the last byte, the first 2 bits in the last byte is also common for all these addresses. So now up to this will be your mask, and the distinction from one address to the other address will be done based on the last 6 bits only here. So the remaining bits are remaining unchanged in this particular block, and hence that will be the default mask here. So this is 8 into 3, 24, 25 and 26 is the mask for this particular block here. So that you are going to specify. So this any address in this followed by a slash 26, then it represents the number of blocks that you are going. No, sorry. So here, sorry, I didn't mention this. So 0, 0 as well as 1, 0 is also common in this. You just see. Only the difference is coming in the last 4 bits, and hence this is the mask. The mask is slash 28. That you can find out by making use of how many addresses that are being used here. So this is represented as 2 to the power of 4. To represent one host here, you require 4 bits. So the least significant 4 bits will represent the host here, and hence the remaining will represent, and that is how you are going to get the first address and the last address in the block here. So any addresses in a any address, it may start with any address, but the first address that is going to be allocated for the block should be integer divisible by this 6, by the size of the block here, and the consecutive addresses are to be given for the block. So this is how any organization will be getting a block of IP addresses here. So now there is a special address which is called as, which is the first address in every network. So first address in this particular network, it is this. So this is the first address for this particular block. This address is a special address which is used to identify this particular network. So this is one network consisting of 16 nodes, 16 addresses. The first address is a special address which is used to identify this particular network, to identify this entire network by the outside world here. So this address will not be assigned to any of the nodes here. And also the last address that you are going to have is with all ones here at the last. This is for broadcasting within this network. So when you want to broadcast to all the nodes in the network, then it will be transmitted as this as the destination address, so that all the nodes in this network will be receiving this. So these two addresses in any network, the first address and the last address containing all ones, and the first address containing all zeros in the host ID are the special addresses. So if it has all the host addresses as a host ID field as 0, then it indicates it is the network address, and if it is all ones in the host ID, then it indicates that it is the broadcast address in that particular network. So a network address is an address that defines the network, that defines the network itself. If it cannot be assigned to a host here, all the host ID bytes are 0 when you go for this network address. So it defines the network to the rest of the internet. That is what we specify. The first address in the block, it identifies the network address. So given any network address, we can find out what is the class to which this particular network belongs to. And so in summary, the first address is a block. In a block is normally not assigned to any device. It is used as the network address that represents the entire organization to the rest of the world. So when you go for these addresses, here we are talking about the network address and the host IDs here. So when you look at the addresses, you are going to divide it into two parts here. The first part is the network ID, and the next part is the host ID. So for this 16 hosts, we require only 4 bits to specify. So these are the least significant 4 bits in the last byte that you are going to use to specify the host ID. So the remaining bits which you have, they specify the block ID or the network ID. So every network address, the block IP address is divided into 2 parts. One is the network ID, and the other one is the host ID. So similar to that of our telephone numbers that we have, similarly you are going to have this IP addresses also. So when you go for this IP addresses, so you are going to have 2 parts. One is the network address and the other one is the host ID. This specifies this particular host in this particular network. So this is the network prefix. The first bits we call it as the network prefix, and the last bits we call it as the host address that you are going to have. So when you go for class A networks, there we have seen the first 2 bytes are used to specify the network, and the next 2 bytes are used to specify the hosts there. So there we have specified the number of hosts that can be connected to any of the block here is 2 to the power of 16. So that is what we have specified. So this is the network prefix, and this is the number of nodes that can be connected in a particular network here. So the leftmost n bits define the network, and the rightmost 32 minus n. If this is n, it will be 32 minus n, because the entire size of this IP version 4 addresses are 32 bit. So 32 minus this network prefix gives the number of bits that we have in the host. So the rightmost 32 minus n bits define the host. This is 2 levels of hierarchy when you go for a IP version 4 addresses. Now we come to the concept of subnetting. Here we have a network. Here there is a network that we have. So here we have we are given with some 64 nodes here, and these 64 nodes are given with addresses 64 IP addresses are given. Those are consecutive. So with the 64 nodes, what will be the network mask here? So the host address, hosts are 64 hosts. So the host ID will be taking how many bits? So 64 can be represented as 2 to the power of 6. So 6 bits will be the host ID that you are going to have. So the remaining bits will be 32 minus 6. So it is 26 bits. So that will be used when you go for this to address any of these 64 nodes in the network here. Of course, the first address will be the address of this network, and the last address you are not going to take it because it represents the broadcast in this. So how many addresses that you can have here? So you can have 2 to the power of 6, that is 64 that we have said. These are the 64 addresses that have been assigned. Now what has been done over here is you have divided it into 3 subnets. The first subnet we are having 32 nodes, and in the second and third subnets we are having 16 nodes each. So total of 64. 32 in subnet 1, 16 in subnet 2, 16 in subnet 3. Then how many bits you require to represent this subnet here? So total here you have 26 is the network prefix now. After that you have 6 bits. So when you look at the addresses that we have here, so say for example, so these are the addresses that so when you represent that, this is the network that you are going to have. So 26 bit is the network prefix and 6 bits is the host prefix that you are going to have. Now what you have done, you have divided it into subnetworks here. So the 32 bits, 32 nodes are divided into, first 32 nodes are divided into subnet 1 say. So when we look at the last byte in binary here, Well, the last byte, the 6 bytes, there is a variation in this 6 bytes in all these nodes which are connected to this network, right? So the 6 bits, if it is 0, the 6th bit, if you take this, if this bit is 0 and then followed by all the other rest bits, so if all these bits are zeros first, then it holds a value of, it will be having a value of 32 there. So what will be the value? 1 followed by 0 followed by zeros. 0 followed by all zeros here is 0 here. And so this is starting over here from 0, 1, 2, 3 and so on up to 31 is being assigned for this particular subnet 1. So here this is 0 followed by all zeros. Then it can be 0 followed by all ones. That will be the end of this particular subnet 1. So when it starts with 1, so that comes to 32 values over here. So when it becomes 1, then again you are going to allocate it to next subnet here. So how are you going to distinguish this first subnet from the second subnet? So the first 32 values in this will be deciding that they go to subnet 1. So that will be dependent based on this 6th bit from the left. So this bit, if it is 0, it indicates it is subnet 1. If it is 1, it indicates that it is either subnet 2 or subnet 3 here. So based on this, you are going to decide this, because half of this you have given it for this subnet 1. So half of this is 32. 32 are the nodes that we have in this subnet 1. So to represent 32 bits, you need to have 2 to the power of 5. That is 5 bits are required to represent these 32 bits. So out of the 6 bits, which is the host ID, 5 bits are used to represent one of these nodes in the network here. So what will be the remaining bit here? So this is the remaining bit. That should hold a value of 0 if you want to represent to this subnet. And if it is 1, then you can refer to any of these 2 subnets. But in these 2 subnets, if you take, every subnet is having, so it moves here when you go for supernetting, and when you go for subnetting, dividing, so the hosts are divided into number of groups here, and hence the number of bits in the subnet prefix will be increased. When you group number of nodes together, that is what we call it as a supernetting, then we will be having less number of bits in the network mask here. So when you go for subnetting, the number of ones in the subnet mask increases, and when you go for supernetting, the number of ones decreases in the subnet mask here. So this is about subnetting and supernetting. So there are a few points that we have to remember, that for any given IP address in its network is obtained by setting all its host ID part to 0. That is the first address of this first address of a network. We call it as the IP address of that network. So when you go for that is what I was telling. So in this, if you are going to set all the bits as ones, the least significant, the host IDs as ones, then it is for some broadcasting. So direct broadcast address is obtained by setting all its host ID parts to 1. So all the host ID parts, if they are set to 1, then we call it as a direct broadcast addresses. So on a particular network, if you want to broadcast it, then cannot be accommodated here. So if you want to accommodate more than 2 to the power of 32 nodes, it cannot be done here. So what is the solution? The solution is just to increase the size of the network address. But before that, what has been used is network address translation as a temporary solution for this. So what they have done is they have identified a range of IP addresses as the addresses for private networks. So these are the private addresses, the range of private addresses. 10.0.0.0 to 10.255.255.255. These are 2 to the power of 24 addresses. These are the private addresses. And these are also the private addresses. when you are making use of these private addresses, when you want to refer to a particular node with this address, it cannot be identified. That is only within the private network you can have these addresses. But when you want to communicate publicly, these addresses cannot be used. So the other addresses which are not in this range only can be used as the public addresses. So these are limited to the organization. They can be distinguished within the organization when you make use of these private addresses. So these private addresses can be used by more than one organization simultaneously because it will be having local significance. So to the outside world, you will not be able to identify a node with this particular private address. So within this network only, within your corporate network or within your organization, you can identify these nodes with these IP addresses in the private addresses. But to the outside world, it will not be, you will not be able to identify this node with these addresses, as these addresses can be used by different organizations for representing their nodes in their network here. So to the outside world, you need to make use of the public addresses only. Public IPs can be used to communicate with the other nodes. But within an organization, you can make use of these private addresses here. So when you want to communicate from this node to the outside world, it cannot be done by making use of this private address. So you need to have a public address for this. So to overcome this address depletion problem, this is the solution that they have given. So this range of private addresses can be given to the nodes in the organization. And this organization may be given with only one public IP. So that public IP will be given to the router. So this is the router here. Here you can see that the router is having a IP address. This is the public IP address that is being given to the router, through which it can communicate to the outside world. So all these nodes, they can directly communicate within their organization, but when they want to communicate to the outside world, so this can be done only by making use of this router. So whenever they have data to be transmitted to outside world, they started this kind of packet this as the source address and the public IP of the other node as the destination address, and that will get to the router here. Now what this router will do, this router, it replaces this address with this public IP, and then it transmits it to the outside world. This is how you will be overcoming the problem of address depletion in IP version 4 here. So this is how it is going to communicate. Here, when you are having a router, this router will be having more than one IP addresses. As this is connected to the outside world, it is having one IP address, and this will be having another IP address connected to this pertaining to this particular network here. So when you want to transmit the packet from this node to the outside world, so it generates a packet with this as the source address and the destination as the remote IP address, and then sends it to the router. Now what this router will do, it makes a note of this IP address. So it makes a note of what is the private IP from which you are delivering the packet to the outside world. So this is the IP, is the source of this particular that is right here, and what is the destination? So the destination is this. So this is the source, this is the destination of this particular packet. So that will be loaded into the label here. So when it is routed out, it replaces this IP address. This is the private IP which will not be known to the outside world. So it has to be replaced with the public IP. So this router is given with the public IP. So it replaces this with its public IP, and then it transmits it to the outside world. And when you get back to this network will be identified with this public IP only. So you will be getting the packet to this router, and now the router will forward this to this. So how do the router forward this to the exact node? So that will be done by making use of this translation table. So here when this node is transmitting the packet to this destination, so this will be the source address and this will be the destination address of this packet. So once the router receives this packet, it looks into what is the source and what is the destination, and then it makes a note of this in the translation table. So and then it forwards the packet replacing this IP address, source IP, with the public IP and to the outside world. And when it gets back the reply for this, then it checks what is the source of this particular packet. So this is the response for the previous packet, so that the source will be the destination address here in the response. So it just looks at this particular source. So then it looks into the translation table for the corresponding source. So this is the source. So to this, the request has come from this particular node here. So it gets a mapping of this. So to this node, the response is coming here with this as the source, and then it will be looking into this table for this external address. Then it gets the corresponding internal address and then forwards a packet to this particular node with that as the destination address. So this is how you are going to make use of this network address translation to overcome the problem of address depletion here. So here we have shown only two attributes in this translation table. Apart from these two, we can have the other attributes also in the table. Like here, this is the private address and this is the external address that is being given. Apart from this, from which port of this private address you are transmitting, and then from which port of this to which port of this outside world you are going to transmit this public address, that also can be specified. And what is the protocol that is being used here? So what type of protocol is the upper layer protocol that you are going to have, that you can store it over here. So these are the 5 columns that you can have in this translation table. So this reduces the address depletion problem, but that is not the perfect solution. So the perfect solution, you are going to get it by increasing the size of your IP address. So the next IP address that is being used is IP version 6 addresses. So this is the next version of IP addresses that are being used here. So an IP version 6 address, if you are going to have, is a 128-bit long that you are going to have here. So previously when you go for IP version 4, it was just 32-bit. So with that 32, the range of addresses that you are going to have is 2 to the power of 32. Now you are having 128-bit long here. So the address space will be 2 to the power of 128 here when you go for IP version 6. And hence, maybe this will not be depleted over a long period here. So when we look at how you are going to represent this IP version 6 addresses, so these IP version 6 addresses, which are of 128 bits, will be represented as 16 bytes here. So these 16 bytes are represented as 22 hexadecimal digits here. So 4 bits are represented as 1 hexadecimal digit. So it will be 32 hexadecimal digits that you are going to represent this. So this is the 128-bit addresses, as you cannot remember all these bits here. So a form of easy representation has to be taken. So it goes for a colon notation over here. So the first byte. So here you are going to have 16 bytes here. So this is the 16 bytes. So after 2 bytes, after every 2 bytes, you are going to have the colon here. So this is 16 bits that you are going to represent in one block here. So these blocks are represented by this colons you are going to have here. So the first 16 bits is this, which contains 2 bytes. FD is 1 byte, EC is 1 byte. What is this F? F is representing 4 bits. The first 4 bits that you are going to have here. This is 1 hexadecimal representation here. So this is the hexadecimal representation of IP version 128-bit addresses. So here you can see that more number of zeros are there. So is it that all these 4 zeros have to be represented? So that can be reduced over here. So this is how you are going to represent it in the form of hexadecimal representation using colon. So hexadecimal colon notation, this is the representation. So you can represent it in binary, but representing 128 bits in binary is a difficult task. So you are going to go for hexadecimal colon representation here. So this again further it can be reduced by not representing all these 4 zeros here. You can represent it as a single zero. Thereby you can reduce the size of this. So this is the abbreviated form. Even the consecutive zeros also may be taken off over here in the similar case, where between two columns you are going to introduce a gap here if you have more number of consecutive zeros here. So when you want to get back this again, so you just count how many number of 16 bits are there. So this is 1, 2, 3, 4, 5. So altogether you need to have 8 were like 8. This is 16 bit that you are going to have 32 hexadecimal digits in total. This is 4 hexadecimal digits. So how many are missing? Then you can have here. So 8 hexadecimal, 4 hexadecimal digits that you are going to have here in total. So here you are having only 5 here. So the remaining are 3. So between these two you can introduce 3 zeros over here. So that is how you are going to represent IP version 6 addresses. So expand this address. So how many 32-bit words are there? 4 hexadecimal digits are there. 1, 2, 3, 4 and 5. So total you should have 8, but you have only 5 here. So you need to introduce 3 number of zeros in between these two columns here, like this. So this is 3 zeros that you are going to introduce. Now you have to represent it as 4 hexadecimal values. So this 0 is represented as single one. So it has to be prepended with 3 zeros here, like this. So 15 is represented. So before this, the byte should be 00. So 0015. In this way, you are going to expand the address. So those are the 16-bit IP addresses that we have here. Now we'll just have a simple exercise here. So a device has 2 or more IP addresses. Then the device is called. So then we have seen at the router, this is given with 2 addresses. One is it is connected to the rest of the internet. So for that it requires one IP address, and this is a device which is connected to this network. So it requires one IP address here. So the answer is a router. So a router is a device which will be having 2 or more IP addresses. But the bridge, it will be working at the data link layer. So it will not be having 2 IP addresses. But workstation is the end node that you are going to have here. So it will be having one IP address. So what is the destination address? When a host with IP address 200.100.1.1 wants to send a packet to all, what is the network ID of the IP address 230.100.123.70? So first you find out to which class it belongs to. So it belongs to class D. So when you go for class D or class E, 230. So the first byte is 230. So it belongs to class D. So when it belongs to class D, you can see that there is no host address and then there is no network address for this. So there won't be any mask for that host for those addresses here. So this, what is this? This one. Not this. Next. Yeah. 230.100.100. What is the network ID? So this belongs to class D. In the class D, there is no networks and the hosts there. Only multicast addresses are there. Only the groups that you are going to specify over there, and hence it does not have any network ID. So an internet service provider has the following chunk of CIDR based IP addresses. available with it. So these are the IP addresses which are available with this. So how many IP addresses are there? That you are going to find out by raising 2 to the power of 32 minus 20. So 32 minus 20 is 12. So you will be having 2 to the power of 12 nodes in this network. The ISP wants to give half of this chunk of addresses to organization A. So half of this chunk, and it sorry for the interruption. So an ISP wants to give half of this chunk to addresses, half of this chunk of addresses to organization A and a quarter to organization B, while retaining the remaining with itself. Which of the following is a valid allocation of addresses to A and B? So now first you find out what will be the mask for this organization A. So for this organization A, what will be the mask? The number of IP addresses that you require for organization A are half of this. So half of 2 to the power of, so this is 20. How many will be there? 2 to the power of 12 nodes are there. So half of this is 2 to the power of 11. So 2 to the power of 11 is nothing but 32 minus 21. So you need 21 bits to represent the mask for this organization A. And for the organization B, you have how many are, so quarter of the organization. So quarter of this 2 to the power of 12 is 2 to the power of 12 divided by 4. So it comes to 2 to the power of 10. These are the nodes that you have in this organization. So the mask will be 32 minus 10. So it will be 22. That is the mask for organization A. So the organization organization A mask is /21 and for B it is /22. So first you need to remove the options which are not included with A for 21, and A should have a mask of 21 and B should have a mask of 22. So these two will be ruled out here. The C and D options are ruled out as the masks are specified as 22 and 21. Now among these two, now you need to find out which addresses will be allocated to A and which has to be allocated to B here. So this, when we look at how you are going to specify this, so there you need to look into the bits in the this 20, after this 20 bits, that is the number of hosts that you are going to have in this network. Then the next bit after this 20th bit, if you take, so I have just given this explanation, you can read afterwards. So when we take this, so the first 20 bits from this will be representing the entire addresses. So when you take that for this organization, if you are going to allocate the after this 128.0, from there if you want to allocate this for class for organization A, then it will be from this to how many it requires. It should have 2 to the power of 11 nodes in this. So from there you have to have. So as we said in the previous case, so this last bits that you are going to have, 12 bits that you are going to have here, will be starting with 0 in the first most significant bit out of this 12 bits. If that is so, then it goes from 0 to all, from 0 to, and all remaining 11 ones, and then it will be going from 0 to all remaining 11 ones there. Zeros to 11 ones. That will be the address that you want to give it to A. So that for that you will be making use of the 21st bit. If it is 0, it will be pertaining to one organization. If it is 1, it has to be to one organization. So when we look at these addresses, so these are 128 and this 128. That is being represented over here. So from this address and this address, this these are the addresses that you are giving, but these addresses cannot be given same for both A and B. So there should be contiguous addresses that has to be given. So you can remove this option, then the option will be this. You just go through this explanation and then you can easily understand how you have arrived at this as the result here. Suppose computers A and B have IP addresses. These are the two IP addresses that are given respectively, and they both use the same mask n. They make use of mask n. Which of the values of n given below should not be used if A and B should belong to the same network? When A and B belongs to the same network, when you apply when you undo the subnet mask, when you undo this network mask to these IP addresses, it should result in the same value. So you undo all this and then you check whether they are resulting in the same values or not. So here you can see that the first 3 bytes are same. So only the thing is you need to verify with the last byte here. So here also the first 3 bytes are same. Verify it with the last byte. So the last byte, what you are going to do, you represent it in binary. This is the binary value for this last byte. And now, and this values, 0 is all zeros in the last byte. When you end with all zeros, you will be getting zeros here. Here also you will be getting zeros. So this will be a subnet mask for this. And the next one, you apply all this. This is 128. So when this is 128, this means 1 followed by 7 zeros. When you add these two, you will be getting the same value here. So this also will be same. And when you go for 192, this will be 1 followed by 6 zeros. This is 192. When you add this, you will be getting the same result. But when you go for this 225, here up to this is same, but here it is different here. So when this 225 is 1110000, so here at this position there will be a variation here, and hence this is the mask that cannot be used if A and B belongs to the same network. Then next, if a class B network on the internet has a subnet mask of 225.225.248.0, what is the maximum number of hosts per subnet? So first you represent 248 in binary and then check how many ones are there in that. And the remaining bits, which are zeros, will be used here to represent the host along with the last byte. So when you represent that in binary, so this is the representation in binary. So up to this is the subnet mask. How many zeros are there? 8, 9, 10, 11. So these 11 bits are used to represent the number of hosts. So the number of hosts that you can have is 2 to the power of 11. That comes to 2048. But as we said, the first address in this will be used to identify this particular network. This is network address that will not be assigned to any node here, and the last address, all ones here in this network, if you are going to have, that will be a broadcast address in that network, and hence these two will not be used. So the remaining maximum number of hosts that you can have here is 2048 minus 2, that comes to 2046. That is the maximum number of hosts per subnet. So you just have to look into this question. What is the maximum number of hosts that you can connect for this subnet is this. But if you are asked with how many number of addresses that you have in the subnet, then it will be 2048. Next, the address of a class B host is to split. Here I am making use of the concept of supernetting, you just see. So the address of a class B host is split into subnets with a 6-bit subnet number. What is the maximum number of subnets and the maximum number of hosts in each subnet? So here, sorry, this is not supernetting. A class B is split into 6 subnets here. And what is the maximum number of subnets and what is the maximum number of hosts that you are going to have here? So in the class B, you can see that the first 2 bytes are specified as the sub network here, and in that network you can have these number of hosts here. But what is that is used? You are making use of 6-bit subnet here. So these 6 bits are used to represent the subnets here. So how many subnets you can have here? 2 to the power of 6 subnets. 2 to the power of 6 is 64. But out of this 64, if all these bits are zeros, then it represents this network here. And all these bits, if they are ones and then followed by all one, that represents the broadcast within this particular network, and hence those two are not used here. So it is only 62 subnets that you are going to have. In that subnet, in every subnet, how many hosts that you can have? These are the number of bits that you will be used to represent the host. This is 8 plus 2, 10. So this will be 2 to the power of 10. These number of hosts can be connected. But out of this, within the subnet, if all these bits are 0, then it indicates that particular subnet, and if it is all ones, then it indicates broadcast within that particular subnet here, and hence these two are not used here. So the remaining are 62 subnets, and then in every subnet you can have 2 to 10, 22 maximum number of hosts connected in each subnet. So the subnet mask for a particular network is 255.255.31.0. Which of the following pair of IP addresses could belong to this network? So what is that you have to do here? So this is the subnet mask that is given, and this with this subnet mask, and then you check the result. So as these two bits are all ones here, so the first 2 bytes, if they have the same value, then they can have the subnet mask. First you just eliminate those options which do not have the same first 2 bytes here. So these two are the first 2 bytes, and these two are the first 2 bytes in this. They are having say different second byte here. So this is not the option, as it is having 2 all ones over here in the first 2 bytes. So this is not the option. So maybe this, or this may not be there, because this second byte is different from that of this. So this is not there, but this can be the option. So this is how you try to eliminate the options. So these two are the options. So now when you want to find which of these two, then the remaining 2 bytes that we have, you expand this in binary, and this also you expand it in binary, and then AND it. So if they result in the same value, then those IP addresses belong to the same network. This is how you are going to find out. So when you AND this, these two will be resulting in the same value here. So same address. So that is how you are going to find out whether they belong to the same network or to this network or not. So an organization has a class B network and wishes to form subnets of 64 departments. The subnet mask should be, what will be the subnet mask? Class B addresses. So when you are going to have class B addresses, so the first 2 bytes are specifying the network. Within that network, you need to divide it into subnetworks here. So how many subnetworks should be there? 64 subnetworks has to be there. So you need to divide it into 64 departments. So how many bits you read to represent these 64 departments? So to represent these 64 departments, I require 2 to the power of 64. So 6 bits. So in the next byte, the first 6 bits are to be ones, and the remaining 2 bits will be zeros for the subnet mask here. So that comes to a value of 252. So this is the network address, and this is the host addresses that you have in class B networks. When you want to represent 64 departments, the most significant bits of the first byte of this third byte will be used to represent the subnetworks here. So these are the subnetworks. 6 bits are used to specify the subnetworks here, and the remaining will be used to represent the hosts within this subnet. So this will be the subnet mask here. So all ones and then followed by zeros. So this value, when you take, it will be 255.255.252.0. That is the subnet mask for this each subnet over here. Which of the following can be used as both source and destination IP? So when we look at all these options, this option in the last bit you can see all ones here. When you have all ones, it is a broadcast address. So it cannot be used to specify a source on the destination. It can be used to specify the destination, but it cannot be a source. A source should always be a unicast address. So it cannot be a source. This one also cannot be a source as it is local broadcast address. So this is not the option. And when we look at this is a loopback address here. So this is also not the option. So the remaining one is 10.0.0.1. So that can be used for both source as well as the destination IP. So which of the following IP address can be used in WAN? So for this, what you have to look into is you need to look into the private IP address spaces over there. So if you are making use of these private addresses, then they are local to a particular network here. So they cannot be used as the IP addresses in the WAN. So that you have to consider. So these two are falling in the range of private addresses, and hence these two cannot be used in a WAN. That is the public IP here. So the only public IP here is 15.1.5.6. So that you can check it by looking at this private IPs here that are being mentioned, range of private IPs. So which does not fall within this range that can be used as the IP address in the WAN. Those are the public IPs. So that can be used here. So the last question. In class B, if subnet mask is this, the total number of networks that can be joined. Here we are making use of the concept of supernetting. So when you look at the subnet mask of class B, it is 255.255.0.0. Now what has been done here? Here number of networks are being grouped together, and then this is giving a subnet mask over here. So what has been done here? I'll just see. So the subnet mask for this will be this. So why? Because if the subnet mask is this, so actually it should be the subnet mask 1111111 all this, but consecutive all these nodes are being combined. That is how many bits are actually this should be 255 mask. 255.255.0.0 is the subnet mask for B, but now it is given as 192. In the sense, there are networks which are combined together into the big network here. So how many nodes, how many networks are being joined, that depends on this subnet mask. So when you expand this is what you are going to get. So actual subnet mask for this is all this second byte is also ones over here. But how many number of ones are being replaced with zeros? 1, 2, 3, 4, 5, 6. So 6 ones are being replaced with zeros when you go for this second byte, which should be always all ones in class B subnet mask, but it is replaced with 6 ones over here in the subnet mask. That means 2 to the power of 6 networks are being combined to form a big network here. So as I said in the previous class, when you are going for supernetting, the number of ones in the mask gets decreased here. So here I am combining 2 to the power of 6 networks here, and hence the number are being reduced by 6 bits over here. So the number of networks that you have joined is 2 to the power of 6. So that comes to 64 networks. So that is the concept of supernetting. So this completes IP addresses. So next we go for IP version 4 protocol here. IP version 4 protocol, and then we'll look at IP version 6 protocol also. So before we go for that, what is the purpose of your network layer? The network layer purpose is to route the packet from the source to the destination. For that, it makes use of the services of the data link layer. So the data link layer is responsible for moving the packet from one node to adjacent node. So on a hop by hop basis, it moves the packets to the destination. But here we have shown only the bottom two layers. But when the network layer is involved, this is how we are going to transmit the packet. So at every node, at every router that we have here, we'll be looking at up to the network layer. So this is at the router, you need to make the routing decision and onto which link it has to forward the packet so that it reaches to the destination here. So for that, it has to look at the network addresses. So every intermediate node, that is the router, will look up to the third layer, that is the network layer. So this network layer is responsible for routing the packet from the source to the destination. So when we look at the network layer at the source, at the router, and at the destination, so this is how the network layer at the router, at the source will be functioning. So what it does, so the network layer receives the data from the upper layer, that is from the transport layer. Then it has to process it. Processing it in the sense, it has to give the source address. It has to add a header over there, which contains the source IP and the destination IP. And then it has to give it to the bottom layer for transmission. So it will be forming a packet and then give it to the data link layer for transmission. So when it is transmitting, here at this source, it has to look into what is the destination of this particular frame packet, and then it has to decide onto which link it has to deliver the packet. So for that purpose, you will be making use of this routing table. So this routing table, it specifies at what is the next hop for this packet to reach to this destination. So that will be given to the data link layer. So that is what is done at the source. And when you look at the destination, when you get the packet from the data link layer, now you have to remove the header. It checks whether this destination address matches with this or not, and then it verifies whether it has received properly or not, and then give it to the upper layer for processing. So this is done at the destination. And what is that is done at the router, at the intermediate nodes here. So at the router, what is that is done is, as soon as it gets the IP packet, it just looks into the destination address. So for this destination address, what is the next hop it has to take? That decision has to be taken at this router in consultation with the routing table. So based on the destination address, it looks into the routing table, and then it finds what is the next hop it has to take here. So onto which link it has to deliver the packet. Then forms a packet and then give the packet to the bottom layer for transmission here. So that has to be done at the router. So switching at the network layer in the internet makes use of the datagram approach to packet switching. So here when you go for this IP protocol, it is a connectionless protocol that we have. And that this IP protocol, it goes for best effort service. It does not offer any sort of error control or the flow control. Error control is done only for the header. We'll see later how it is. So the communication at the network layer in the internet is connectionless here. So all the packets may not be routed via the same path to the destination. They'll be routed on different paths here. So when we look at this IP version 4 protocol, so this is the protocol that is run at the network layer. So at the network layer, you will be having this IP protocol being running. So here you can see at the network layer in the TCP IP protocol suite, along with this IP, you have 4 more protocols that are running at the network layer. ICMP, IGMP, ARP protocol, as well as RARP protocol. So this ARP protocol is the address resolution protocol, which is used to map the IP addresses into the physical addresses. Later we'll see what is the use of this. And so these are the other protocols here. So these two are shown, IGMP and ICMP are shown above this IP, and RARP and ARP are shown below this. In a sense, this the packets that are coming from these two protocols makes use of the services of IP. But these two protocols do not make use of the services of IP. They will be making use of the services of the data link layer here. So that is why these two are shown below this IP protocol here. So this is the protocol that is run at the network layer. And this IP protocol is a connectionless protocol that we have, and it offers best effort service. It does not provide any sort of error control and the flow control. If you want to achieve reliable data transmission, then at the upper layer you should have a reliable protocol here like the TCP protocol. So when you go for this IP version 4 protocol, so what is that it is going to do? It adds a header to the data here. So the data that is coming from the upper layer, to that a header is added here. So when we look at the format of the datagram, so the packet at the IP level, we call it as a datagram. So when we look at the format of the datagram, this is the IP version 4 datagram format, where the header is a variable length header that you are going to have, which ranges from 20 to 60 bytes. That is the header. That is followed by the data. So the total length of the data, the total length of the header and the data, the total size of this IP packet is a maximum of 65,536 bytes. And this header is 20 bytes. So you can deliver only the header also here, so that the total minimum size of the data that has to be delivered is 20 bytes, and then it can go to a maximum of 65,536 bytes here. So when we look at this header, what is this header? So the header is variable in length that we have said. It can be from 20 to 60 bytes that we can have here. So in any protocol, in all the protocols, when you go for this IP protocol or TCP or UDP protocol headers, these headers are represented as 32-bit words. So this is one 32-bit word and this is another 32-bit word. This is how you're going to represent the headers here. So when we look at the first word, in the first word, the first 4 bits of this header specifies the version. So what is the version of this IP packet? IP. So it can be either 4 or 6 that we are making use of. Currently we are making use of 4 here, but in the near future it will be IP version 6. For that, a different header is defined. For this, the header value of for this version should the version value for this in this header should be 4 here. So that is represented as 0100. That is the binary for this 4. And then the next 4 bits specifies the length of the header. What here, why this field is required is, you can see that the length of the header is varied from 20 bytes to 40 bytes here. So for this purpose, you require this header length. This is represented using 4 bits. But the value that you are going to represent here in this header length is in terms of 4 bytes. In the sense, if this value, if the header size is 20 bytes, but you will be represented as 4 bytes. How many number of 4 bytes that you are going to have in the header? That is 20 divided by 4. So it takes a value of 5. So the header length value will be 5 if the length of the total header is 20 bytes here. If the minimum value this header length takes is 5, and the maximum that it takes is, the maximum length of the header is 60. 60 divided by 4. So it comes to 15. So that is the maximum value that this header length will take here. So this is represented as a number in terms of 4. The size of this header in terms of 4 bytes. That is what you are going to represent here in the header length. Then followed by the 8-bit service bits. So these service bits are specify what type of service that is required for this particular data, or the upper layer protocol data that you are going to transmit. So this service type are currently it is used as the differentiated services. So in the old versions it has been used as this service type. So which is 8 bits that we have here. These are the 8 bits that we have here. The first 3 bits in these 8 bits specifies the precedence. So here, what is the priority of this packet? that will be specified in this first 3 bytes, this precedence. And the next 4 bits are used to specify what type of service that we require. At any one instance of time, any one of these bits can be 1. When 1 is 1 and the remaining bits have to be 0 here. So this, when you have all these 4 bits DTRC as 000, then it is the normal traffic that you are going to have here. And when this particular D bit is set to 1, it implies that it is minimized delay. So the packet that you are going to deliver has to be delivered with minimal delay. So that is when this particular bit is set to 1. So that is this is minimized delay. And the next bit is maximize the throughput. So when this particular bit is set to 1, the throughput has to be increased. These are maximum reliability. So without any error, without any dropping of this packet, it has to reach to the destination. That is maximum reliability. And the last bit is minimize the cost. With less cost, you need to deliver this packet. So these are the 4 bits which represents the type of service that we require. The last bit is not used in this service field. And in the present scenario, it is used as this code point, and the last 2 bits are not used here. So the first 6 bits are being used. Among these these 3 bits, the first 3 bits if you leave, the second 3 bits if you are going to have it as all zeros, then it is compatible with the old service type. And for the remaining bits, if you are going to have these values differently, they can be used to specify the differentiated services, which can be assigned by the internet authorities or something. So, but mostly this service type field is not being used so far, is not in use mostly here. And then the next 16 bit specifies the total length of the packet. The total length of this packet in bytes, that will be specified in this total length, including the header. So including the header plus the data, this gives the total length of the packet that you are going to transmit. So this total length is 16 bits. With this 16 bits, you can hold to a maximum of 2 to the power of 16. So 2 to the power of 16 minus 1. So that is the maximum limit of this IP packet. That is 2 to the power of 16 minus 1 comes 16 comes to 65,536. So the last byte will be 2 to the power of 16 minus 1. So it will be 65,535 is the number for the last byte here. So because the length of this total length is 16 here, you can have a maximum of 65,536 bytes, including the header. So when you want to get the size of this data, what is that you have to do? Total length minus the length of the header gives us the length data here. And the next 3 bits, identification, flags, and the fragment segment, these are used for fragmentation. So this packet 65,536 is the size of the packet that you are delivering. But if you want to deliver it over an Ethernet, in the Ethernet we know the maximum size of the packet can be 1500. So that is the maximum payload that it can handle. But if you want to transmit this size packet over this Ethernet, it will not be possible. So for that purpose, based on the underlying network, you need to fragment this entire packet into several fragments based on the maximum transmission unit of the underlying network. So for that purpose, we will be making use of these 3 fields. We'll see later what these fields are. So next field is time to live field. So time to live, which is 8 bits in size. Here you are going to specify the number of hops here. So how many number of hops this packet has to die, that you are going to specify in this time to live. So if you are not going to have this field, what happens? This packet may be looping around in the network here, and hence there should be an end for every packet here, and hence you are going to go for time to live. Within that time, it reaches to the destination. So if it is going to hop, what it does, it creates some loops over there, and hence you need to have maximum time for this packet to live here. That you are going to specify in number of hops. So on every hop, when a packet reaches from this node to the next switch, then at this switch, this count gets decremented by 1. So on every hop, it gets decremented by 1. And when it becomes 0, that particular node which sees that the time to live is 0, then it simply drops that particular packet. So at every hop, it is decremented by 1. And when a node finds that it is 0, then it simply drops this particular packet. Thereby, you won't have duplicates in the, thereby this packet will not be looped in the network for a longer period of time. The next 8 bits specifies the protocol. So what is the upper layer data that this particular packet is carrying? That is the protocol field. So that protocol field can take these values. So as I said, so there are two protocols which we have in the network layer which makes use of this IP services. Those are ICMP, IGMP, and along with this one routing protocol like the OSPF also makes use of the services of IP protocol here. So you can get the data from any of these protocols to this IP protocol here, and hence you need to distinguish one from the other. So if this protocol field holds a value of 1, then it specifies that it is carrying ICMP packet. If it has a value of 2, it is IGMP packet. If it is 6, it is TCP packet. If it is 17, it is a UDP packet. And if it is 89, it is a OSPF packet. Like this, you are going to differentiate what type of data is being carried in this particular IP packet. So that is the protocol field. And the next 16 bits specifies the checksum. Here the checksum is calculated only on the header, not on the entire packet here. Only for the header you are going to calculate the checksum. So it is offering only error control over the checksum, not for the entire packet here. So that is header checksum, which makes use of this checksum concept over there, where you are going to divide this entire data into 16 bits, and then you are going to perform once complement addition on all these 16 bits, then complement it. So that is how you are going to calculate the checksum here. So then the next 32 bits specifies what is the source IP address of this packet, and the next IP address, next 32 bits specifies the destination address. So this is the mandatory header. So this is the mandatory header which comes to 20 bytes. So here 1, 2, 3, 4, 5 32-bit words. That is nothing but 20 bytes. 5 into 8. Sorry. 5 32-bit words, 5 into 4. So that comes to 20 bytes. So, and you can have an options here which goes to 40 bytes. So this mandatory header is of 20 bytes and the remaining 40 bytes may be optional. That is why the length of the header is varying from 20 bytes to 60 bytes. So it can have a minimum value of 20 bytes and a maximum can be 60 bytes header that you can have. So now we have to look into these three fields: identification, flags, and the fragment offset. So now before that, we'll just have simple examples here based on the first 8 bits. So what are these first 8 bits? This is the version and this is the header length. The version bit is 0100. That is the IP version 4. And the next 4 bits specifies the length of the header in 32-bit words here. So here, when you go for this, the first 4 bits specifies what is the version of the IP. So this version is 4. And what is the next 4 bits? The next 4 is the header length. So when you convert this into decimal, so this will be 2 power 0, 2 power 1. So this has a value of 2. So 2 into, what will be the header length, total header length? 2 into 4. So 8 bytes. So, but 8 bytes the minimum header length is 20 bytes, but now it is giving a value of 8 bytes, and hence the receiver discards this particular packet. The next question, in an IP version 4 packet, the value of header length is 1000 in binary. So when you convert this into decimal, what is that you are going to get? 2 power 0, 2 power 1, 2 power 2, 2 power 3. 2 power 3 is 8. 8 into 1 is 8. So it comes to 8. Value of 8 in the header length. That implies 8 into 4, 32 bytes. So 32 bytes is the length of the header. So among this, how many bytes of options are being carried? The mandatory header is 20 bytes, but now it is carrying 32 bytes here, 32 value here. So 32 minus 20, so 12 bytes is the option that you are going to have in the header length. 12 bytes is the options that you are going to have in the header. In an IP version 4 packet, the value of header length is 5. And the value of the total length field is 0x0028. How many bytes of data are being carried by this packet? So first, the header length field is 5. So how many bytes? 5 into 4, 20 bytes is the length of the header. Now the total length is 28. This is in hexadecimal. Now you convert this hexadecimal into decimal. So 16 to the power of 0 into 8 plus 16 to the power of 1 into 2. So that comes to 16 plus 8. 16 twos are 32, 32 plus 8. So it will be 40 bytes. That is the total length of the packet. So what is the length of the data? The length of the data is total length minus header length. So the total length is 40 bytes and the header is 20 bytes. So it will be 40 minus 20. So it will be carrying this 20 bytes of data. So this is how you have to calculate here. An IP version 4 packet has arrived with the first few hexadecimal digits as shown here. This is represented in hexadecimal. Hexadecimal in the sense one decimal value will be represented as 4 bits. So this is 4. That is nothing but 0100. So this represents, the first 4 bits represents the header length. So that, version. So this is version 4. The next 4 bits is 5 here. That represents the header length. So 5 is the header length. So the header length is 5 into 4, that is 20 bits. Now, what is required here? So this is 1 byte, this is 1 byte, this is 1 byte, this is these two digits represents 1 byte here. So how many number of hops can this packet travel before being dropped? That is asked. So first you just look into the header. After how many bytes you are going to get this particular time to live field. So this is 4 bytes. This is 4 bytes. So after 8 bytes, the 9th byte specifies the time to live field. So in this you just calculate what is the 9th byte. So this is 1 byte. Two digits form 1 byte here, because it is represented in hexadecimal. So this 1 byte, these 1 byte, 2, 3, 4, 5, 6, 7, 8. The 9th byte specifies the time to live field. So the time to live field is 1. So after 1 hop, this will be dropped. So this means that the packet can travel only 1 hop. So the data belong to what upper layer protocol? So the next byte, 10th byte, it specifies what is the upper layer protocol. So this holds a value of 02. So when we look at what is this 02 here, so the 2 is representing IGMP protocol. So this is carrying IGMP protocol. So this is how you need to analyze the values in the header. Now, so far we have seen all these bits, and now these fields are remaining: identification, flags, and fragment offset. As I said, this entire frame cannot be transmitted in a single as a single unit when you go for different networks, as the different networks offer different maximum transmission units. So this IP datagram has to be embedded into a frame at the data link layer. But the data link layer, it imposes a maximum size on the frame length here. So it cannot be embedded into a single frame here. So when we look at various protocols, so these are the various protocols. We have seen this Ethernet protocol. Ethernet protocol, it imposes a maximum restriction that the maximum transmission unit, that is the maximum payload that it can support is 1500 bytes, not beyond that. So these are the other protocols that are supporting various lengths here. So when it is supporting only 1500, but your datagram is of size 65,536 bits, it cannot be transmitted into a single here. So it should be divided into number of fragments, and then it has to be given to the data link layer for transmission. So when you have divided your datagram into number of fragments, how do I identify which fragment is the first fragment, which fragment is the last fragment, and how many fragments you have? So one after other, which is following, all this has to be identified. To identify all this, the three fields are being used over there. Those are identification field, which is of 16-bit in size. This 16-bit field, it specifies what is the ID of this particular packet. So when you have divided this particular datagram into several fragments, all the fragments carry the same ID value, so that at the destination, when you want to group all these segments together, then that will be grouped based on this identification number only. So this identification specifies that all these fragments belong to a particular datagram. So all the fragments pertaining to a particular datagram will hold the same identification value here. And the next 2 bits, based on these 2 bits, you are going to identify one after other what are the fragments that are following here. So all these fragments will be holding the same identification value. And the next 3 bits are specifies the flags, and the next 13 bits specifies the fragment offset. So that we'll discuss now. So when you go for this 3 bits in the flags, so the most significant bit out of this is not used, and remaining 2 bits are used here. One to specify don't fragment, and the other to specify more fragments. When this particular bit is set, don't fragment is set by a particular network, then it indicates that at any cost, this particular fragment should not be further fragmented. So if this bit is set to 1, it indicates that at any network, if at all it cannot deliver this entire fragment, it cannot be further fragmented. That will be identified. That will be decided based on this don't fragment. If this field is set to 1, so it cannot further fragment it. If a particular node cannot transmit, if that particular network do not support this size, then as this particular do not fragment bit is set to 1, it cannot be further fragmented, and hence simply that particular node drops this packet and sends an ICMP message, an error message to the source indicating that it has dropped this packet because it cannot hold this particular, it cannot process this size fragment. And the next bit is M bit. It indicates more fragments. As you have fragmented when we have fragmented a large datagram into number of fragments, so if a fragment has a fragment to be following S, then this particular bit is set to 1. So for the last fragment only, this bit will be set to 0. If it has only a single fragment, then also this bit will be set to 0. So this bit will be set to 0 when it is the last fragment, or it is the first fragment and no further fragments are there. That is, it is the only fragment, then this bit is set to 0, or if it is the last fragment among the fragments, it will be set to 0. For the remaining fragments, it will be set to 1 here. So here, how are you going to specify the offset? So when you have divided a large message into number of fragments here, then you need to specify what is the offset. Here you have 3999 bytes, say. So this is the byte 0, and for the you have divided this into say 1400 bytes each. So the first 1400 bytes form the first fragment. So I need to indicate this fragment with a fragment offset. So that will be the first byte. This is the first byte in the entire fragment, in the entire packet. So this fragment offset indicates at what position you are going to have this particular fragment in the entire datagram. So that you are going to specify in the fragment offset. So here you can see this 4000 bytes are divided into 3 fragments here. So the 1400 bytes forms the first fragment. So this will be from 0 to the, please Archato, 0 to 1400. So this is the fragment, this is the first fragment. It is carrying 0 to 1399. So what is the first byte? This is starting at 0. So the first offset is represented as 8 byte. 8 is represented as 0 divided by 8. So this comes to 0 value. So that is represented in 8 bit as 8 byte values over here. So this is represented as 0 divided by 0. So that is the first fragment offset. The next fragment is starting with, once this is completed, 1400 bytes from 0 to 1399 are transmitted. The next fragment, the next bit starts from 1400. So that will be forming the second fragment here. So what is the starting bit here? 1400. So to indicate this particular fragment, the fragment offset will be 1400 divided by 8. So the offset is represented as 8 bit values over here. So that is 1400 divided by 8. So it comes to 175. So this holds a fragment size of 175. The offset will be 175. So once 1400 is completed, then it starts with 2800. So this is how you are going to set the offset fragments. So that is represented as the first fragment number divided by 8. So to get the first fragment number, this offset is multiplied by 8. Then it gives the first byte in the fragment here. So here, this is the detailed fragmentation example that we have. So this is the identification number. This is followed by the flag. The most significant bit is not used. This is for don't fragment. That bit you are not considering over here for fragmentation. You are considering only more bit field, more bit here. So this more bit is 0, indicates that this is the only fragment that it has. So at a particular network, when it has reached, if it is not supporting this size fragment, this 4020 is the size of the packet. So the size of the packet, the length of the packet is 4000 and the header is 20 bytes here. So this is not supported at a particular switch, say, at a particular router. So this has to divide it into 1400 fragments, say 1400 byte segments each, say. So then this particular 4000 bytes which you have now has to be divided into 3 fragments, each of 1400 here. So the previous example we have seen, for this only you are representing this in the form of packets here. So this identity will be carried in all the further fragments here. So 1457 is the identity for this particular for this particular datagram, which is fragmented here. So all the fragments carry the same ID here. And then this bit is 0. Now it is divided into 3 fragments. So in this, the first fragment, the bit is set to 1, indicating that there are some more fragments following this particular fragment here. So then this bit, so it holds the values from 0 to 1399. So this is the 1400 is the size of the data that is being transmitted. So for every fragment, you will be having a header. So this will be 1420, including the header. That is the size of the first fragment. And the size of the second fragment is also 1400 bytes plus 20 bytes is the header that you are going to have. Here you can see that the offset here is 175. How you have calculated this? This is based on this. 1400 is the starting byte here. 1400 divided by 8. So that comes to 175. So that is the value that you are going to have it over here. So the next fragment. So up to this you have transmitted 2799. 2800 byte is the next byte that is to be transmitted in fragment 3. So for that the offset is 350. And this is the last fragment. It has been divided into 3 fragments. So the more fragment field is set to 0, indicating that this is the last fragment in this. So here this fragment, when it is passed over a network, again it has encountered a network which cannot carry this 1400 bytes. Then again it is further divided into 800 bytes fragments here. So the first 800 bytes in this 1420 bytes here, from 1400 to 2799, is sent as one fragment here. So this is further fragmented. So this is 1400 to 800. When you add 800 to this, it will be 2200. So the last byte will be 2199. That is carried in this fragment here. So this fragment is further fragmented. So now this more bit is set to 1 here because it has some more fragments to be followed here. And then here, so the starting address is 1400 byte here. So 1400 divided by 8 is 175. In this fragment, it is further divided. So up to 2199 it is sent in this fragment, and 2200 will be sent in the next fragment here. So 2200 divided by 8, it gives 275. So that will be the next fragment offset here. So these 2 bits are set to 1 because the fragment which is fragmented is not the last fragment. It has some more fragments to be followed, and hence when this fragment is again fragmented, these bits will hold the value of this only. If it was 0 and then it is divided into 2, then this fragment would have 1 and this would have got a value of 0 here in the more fragment. Is it clear? So for example, if this is divided into 2 further, then the first fragment will hold a bit more flag value as 1, and the last fragment will hold a value of 0 here. So this is how you are going to represent these 3 fields here. Identification field, the flags field, and the last one is the offset field. So this is how you are going to fragment a large datagram into segments over here, and then these segments, this segmentation will be based on the underlying network. So here we have a simple exercise here. A packet has arrived with an m-bit value of 0. Is this the first fragment, the last fragment, or the middle fragment? Do we know if whether the packet was fragmented? So as it is having a value of 0, it cannot be a middle fragment because it do not have any further fragments following this. So this can be a last fragment or a first fragment. So, but how can you decide whether it is the only fragment or is it the last fragment that you are going to have? So we cannot decide whether it is a first fragment. If it is a first fragment, that it says that it is the only fragment that you have. Or it can be a last fragment because the value is set to 0. If it is having only one fragment, then it also have a value of m bit set to 0 here. So a non-fragmented packet is considered the last fragment. That is how we cannot decide whether it is a first fragment or the last fragment. A packet has arrived with an m-bit value of 1. Is this the first fragment or the last fragment or a middle fragment? Do we know if the packet was fragmented? Here, as the m value is 1, it indicates that there are number of fragments here. So it is fragmented, that we can come to know. But we cannot decide whether it is the first fragment or the middle fragment. It cannot be the last fragment because for the last fragment, m bit has to be 0. So it cannot be the last fragment, but it can be the first fragment or it can be the middle fragment. That also cannot be decided from this. Now, a packet has arrived with an m-bit value of 1. and a fragmentation offset value of 0. Is this the first fragment, the last fragment, or a middle fragment? How do you decide on this? So first, the m bit is 1. It indicates that it is not the last fragment. And now you look at the offset. The offset value is 0. This is 0 only for the first fragment, and hence this is the first fragment. Is it clear? So based on this offset value, now you can specify whether it is the first fragment or the middle fragment. It cannot be the last fragment because the m bit value is 1. So it cannot be the last fragment. It should be either the first fragment or the middle fragment. So to decide on this, we'll be looking at this fragment offset. The fragment offset is 0 only for the first fragment, and hence it is the first fragment that is transmitted. Now, a packet has arrived in which the offset value is 100. What is the number of first byte? What is the number of the first byte? Do we know the number of the last byte? So the offset here is 100. So the first byte you will be getting. So the first byte divided by 8 gives us the offset, right? So the offset will be equal to the offset value, the number of the byte will be equal to the offset value into 8. So 100 into 8. So that is the first byte number in this fragment. So it is 800. Can we decide what is the number of the last byte? Here with this data, we cannot decide what is the last byte here. If you know what is the size of this fragment, then you can specify what is the length of the last byte here. So in this example, a packet has arrived in which the offset value is 100. So what will be the first byte number? It will be 800. So 100 into 8. So that is the first byte number. So the value of the header length is 5. The header length value is 5. And the value of the total length is 100. 100 in decimal. And this is 5. Header length is 5. So what will be the header length? Header length will be 5 into 4. So it will be 20 bytes. So what will be the length of the data? The length of the data is 100 minus 20. So that comes to 80 bytes. So the starting byte is 800. Then what will be the last byte? So total it is carrying 80 bytes here. So 100 minus 20. So the data is 80 bytes. So the first byte is 800, and hence the last byte will be 1 less than 880. So that will be 879. So that is the address of the last byte, as it is carrying 80 bytes here. Right? So how to calculate the checksum? So this fields, all when they have filled, including the checksum field is set to 0. Now you divide this entire IP packet into 16 bits each. So first 16 bits in one row, the second bit 16 bits in the other row. Like this you perform bitwise, once complement addition over there, then you take the complement of the sum, and that will be the checksum. Now you store this checksum replacing this 0, and then send it to the other end. At the receiving end, to verify the checksum, what is that you have to do? Including the checksum, you perform the addition on all these values here on a 16-bit values here, and then you check that you take the sum, take the complement of that, and then it should result in all zeros. If it results in all zeros, the complement results in all zeros, then it indicates that we have received the packet without any errors. Otherwise, there will be an error. So that is how you are going to calculate the checksum when you go for IP version 4. So when we look at the IP version 4, here when you look at the header contains a mandatory header of 20 bytes, and it also has a optional header of 40 bytes here. So what are the various options that can be carried in a IP version 4 protocol? So these options are divided into two categories. One is single byte options, which holds only single bytes here, and the others are multiple bytes that you can have. So in this single byte, you have two options here. One is no operation and the other one is end of operation. So when you go for this no operation, if you have more than one header, more than one option that we have, so one option is separated from the other, making use of this particular option no operation here. So that byte is introduced between the options if you have more than one option being transmitted. And end of option is after all the options, the last option will be followed by this end of option byte here. So that indicates the end of options. So when you go for this remaining options, there are four multiple byte options here. Record route option. So this record route option, when it is set, then at every node, intermediate node, it records what is the address of that particular node which it has visited. That will be recorded into the option field here when you set this particular record route option. So if it is traveling a path like A to B to C to D, to reach to D from A, if it is following intermediate paths like B and C, so what are all the intermediate nodes that are reached when the data is delivered from A to D? That IP addresses of all these intermediate nodes will be recorded once this option is used here. And the other two options, strict source routing and loose source routing. Here you are going to specify the path. In this option, you are going to specify the number of the path here that has to be followed for this packet to reach to the destination. When you specify that number of nodes here in this route, when you specify that route in strict source routing, all these nodes which are specified have to be reached. Only those nodes have to be reached when you go for strict source routing, right? And if at all it reaches to any other node which is not in this route, then that packet is dropped. If you go for this option, loose source routing, so apart from these nodes which are specified in the route, it can also go to some other node also. But ultimately, all these routers which are specified here have to be reached. That is loose source routing option. And the last option is timestamp option, which is same as that of the record route, except that in the record route only you are going to place the IP addresses of those nodes which are reached during its transmission to the destination. So in the timestamp, apart from this IP address of that node, at what time it has reached that particular node also will be recorded when you go for this timestamp option. So these are the various options that we have in IP version 4 here. So these options can be used here. One or more options can be used, and total of these options should be limited to 40 bytes when you go for IP version 4. So all these options you are going to mention as the optional field in the header here. So the total length of the header can range from 20 to 40 bytes in a IP version 4 protocol header, and this 20 bytes is the mandatory header and 40 bytes is the optional header. So the next one is IP version 6 protocol. So this we'll see tomorrow. So for today, I'll stop it here up to IP version 4 header. So you just have a look at all the fields in the IP version 4 header, and then thoroughly you go through this exercises, and then you try to analyze the header, IP version 4 header. So in the next class, we'll look at IP version 6 header, and then we'll look at some of the problems that are given in the gate. So thank you. So if you have any queries, please do post. Please do post in the link that is given. So if anyone have posted, I'm just looking at this. So as of now, I have not received any queries. So maybe if I have the queries tomorrow, I'll answer them, and then we'll go ahead with the next class tomorrow. Thank you.